So hi everybody, today I'll be sharing my presentation on automatically discovering and generating visual design characteristics. This is joint work with Alex Purnap and Vinit Kumar, both at Yale. This was done while I was doing my PhD with these advisors. So to start with, I think you already saw in the first talk that a lot of marketing depends on the visual imagery. And that is because when people go and buy these types of products like cars, fashion or furniture, they are not just buying the products based on the performance characteristics. You're not just looking to buy a car based on its fuel efficiency, based on its power, based on the space, but you also go and choose a car based on how it looks. Typically in marketing and economics literature, it has been very hard to somehow incorporate visual aesthetic designs into models. And this is one area which I'm hoping to bridge through this work. So the goals of this project are three. So the first overarching goal is that we want to obtain interpretable visual characteristics directly from images. We want to do it in an automated fashion. Second, we want to quantify all of these characteristics. And third, we want to then generate visual designs that span the space of visual characteristics. So to put it in a different context, suppose we have a data set which is of hundreds or thousands of images, like the one I have over here in the automobiles. So I want this method to discover or find the visual characteristics, quantify each of those characteristics, so that at the end I have a vector of visual characteristics for each product image. And if I have those vectors for all of the products, then I'll be able to apply this method in perceptual mapping, visual content analysis, product recommendations, etc. And today I'll be talking specifically about visual content analysis application. We have another paper which is more in the spirit of a perceptual map or a market structure. You might think that images have long been used in marketing or economics, but what's really different, in this project? So typically the way people obtain visual characteristics from images vary along two aspects. How automated is the method and how interpretable are the characteristics. So a method like PCA, which has been there for a long time, is automatic, but it does not yield interpretable visual characteristics. On the other hand, recently a lot of literature in marketing has used methods which are interpretable, in the sense that a researcher will decide which visual characteristic probably drives their dependent variables, so they have some hypothesis, and they obtain those visual characteristics then from some deep learning pre-trained model, and then go and do that. So that's not automated because it requires researchers' judgment. However, by definition, it's interpretable. Now, our method is based upon disentanglement learning, which has both of these properties. That is, it is automatic as well as it yields interpretable visual characteristics. So a bunch of papers, I won't go into the details. Some follow under automatic but not interpretable, and some follow in the other opposite bucket, manual but interpretable. So the roadmap of our approach is that we use a method known as disentanglement learning. I'll be expanding on that. But it runs into one theoretical result which is known in that literature as impossibility theorem. And the key methodological contribution of my work is to propose a way to overcome that theorem. First, what do we mean by disentanglement? So this is a concept which was proposed by Yoshua Genchio in 2013 as a conceptual goal. And later on, a lot of work was done within deep learning on this type of method, and it can be defined as one in which, suppose you change only one visual characteristic, keeping all the others fixed, then the image should change only in one human interpretable way. So if you look at this image, we have a watch on the left side, and suppose we find a method which gives us a vector of visual characteristics. Then if I fix z2 to zj, but only vary z1, then the image should only change along one human interpretable way. And we can see that the watch is changing along that color. It's getting darker and darker as the value of z1 is increased, while others are fixed. And we can see that the watch is not changing along any other human interpretable way. Similarly, in z2, we see that the watch is changing along strap color, but other aspects of the watch are relatively same. Right. So this is based upon a framework in deep learning which is known as variational autoencoder. This method on top of variational autoencoder imposes statistical independent latent space, which allows it to find human interpretable visual characteristics. So like I said at the beginning, this model runs into a result known as an impossibility theorem, and I'll give you some intuition behind this. So suppose you had two visual characteristics which are statistically independent. Let's say on x-axis you have dial color, and on y-axis you have strap color. Then you can rotate the axis in infinite number of ways, and they will still be statistically uncorrelated. So this result theoretically showed that you need some sort of a supervision on top of this disentanglement learning. So the first solution that machine learning researchers came up was to use some sort of a ground truth, and they were working with synthetic data sets. So suppose you have the size, position, color, and they already had those because those were synthetic data sets. So they would train these models to first find disentangled or these visual characteristics, and they will try to predict size, position, color, etc. from these visual characteristics. Now this was a problem for us because these were the visual characteristics that we intended to find through our research. So we could not use ground truth. And furthermore, ground truth on product images is fundamentally unknown. We are not working in the realm of synthetic data sets. The second problem is, suppose we want to still use ground truth, then we will need to have the researcher to determine what characteristics to focus on. So this will again take us back to the original set of methods that researchers currently use in which they define the visual characteristics. And the third problem is that even if suppose we know some visual characteristics, we would need humans to label these characteristics. There needs to be some agreement. We do not know whether they would understand that. For a watch, a dial color or a strap color might be very, very easily understandable. But in case of a product like car, we find some characteristics which are probably not easily quantifiable by humans. So our solution was to leverage structured product characteristics, and by structured product characteristics, I mean things like brand, things like price, or any other product characteristics like material of a watch, or in case of a car, it could be the engine size or the horsepower of a car. And the hypothesis that we had was that these structured product characteristics might serve as good supervisory signals because perhaps the products differ along how they look based on which brand they belong. So for example, the data set we have was of luxury watches. Perhaps Cartier watches and Rolex watches look very different. So if they do, then they would occupy a different space in the visual characteristic space, and the truly disentangled visual characteristics will be able to separate them out. Another hypothesis was, suppose if brand does not work, price can also work in certain kind of product categories. If products belonging to different price levels visually look very, very different. And I have an example of sneakers over here because we also applied it in sneakers, and we found that price was helping us separate out these visual characteristics. So the model is based, it's estimated using a VAE framework plus an additional supervised loss. And the two key terms that we need to find for our estimation are lambda 1 and lambda 2, which are the weights on these two different losses. The first loss, which is highlighted in red, is known as the total correlation loss, and that is the one which promotes statistical independence. And the last loss is the supervised loss, which takes these visual characteristics and tries to predict some supervisory signal. So in order to find these lambda 1 and lambda 2, we need to train this model over a grid of lambda 1 and lambda 2 and find optimal values of lambda 1 and lambda 2 over some metric. The metric we use is known in the literature as unsupervised disentanglement ranking, and we choose this metric because it does not require any ground truth, which we did not have, and it's based on the notion that if there is a truly disentangled representation, then no matter what the starting point of the optimizer is, it will always converge to something very similar. So you can have a model trained with different random seeds, and if the statistical correlation between different representations are similar, then this metric will give it a high score, and that's the one it will say is the most optimal hyperparameters. This is the architecture, and I won't go into the details, but in case someone is interested, it's also in the paper. So like I said, the dataset that we used was of luxury watches that was auctioned at Christie's. We had the brand associated with each watch, the movement, material, where it was manufactured, where it was auctioned, what was the price that was fetched at the auction, etc. And so these served as our supervisory signals. And I want to emphasize that a priori we did not have a hypothesis over which signal will work better. So we wanted to try out all of them as well as combinations of them. So we found 6 visual characteristics. We found dial color, dial size, strap color, rim color or the bezel color, knob size or the crown size, and we found dial shape. So there could be more ways along which a watch varies, but these are the 6 characteristics that our method said were probably varying the most in our data set, and it was clearly able to find all of them, and we received a numeric number for each watch. We received a number for all of these 6 characteristics. Next, we wanted to investigate why does a particular signal, why is it able to separate out or do better on visual characteristics. So for this, we tried to, in a way, drew the distribution of visual characteristics for different brands, and we saw what was the GS divergence metric, the difference between different brands, and we saw that GS divergence metric was very high for brand, but when we did the same thing for price, we found that the distributions between different price levels was not so high. So what it means is, in these luxury watches were not so different at different price levels visually, but they were very different across brands, and that is why brand was serving as a good signal. Now in sneakers we found the opposite. I don't have the result, the table over here, but we essentially found that price was serving better, and we could also investigate why, and one of the visual characteristics in sneakers was the sole color, and we found that low price sneakers were mainly having white sole color, but as the price of a sneaker goes up, it started to have color. Because we obtain a vector of visual characteristics, we can also draw a distribution of dial color in our data set, and this is what it looked like. So we could see, how many light colored watches are there, light dial colored watches. Similarly, we could see the proportion of dark dial colored watches in our data set. This was the distribution for all the 6 characteristics. So to come back again to our research goals, we wanted a method to automatically discover interpretable visual characteristics, to also be able to quantify those characteristics. So these 2 goals were satisfied, with whatever I've shown you so far. The third goal was to generate visual designs that spans the space of visual characteristics. Now you will already see on this row that I'm showing you at the bottom, that I am changing a visual characteristic, and I am also able to generate a different watch. Essentially, because this is an encoder-decoder model, so it's able to decode images from those visual characteristics. Now, leveraging this property of this model, we conduct a choice-based conjoint in which we give the method different vectors of visual characteristics. It would generate different watches. So we would give the method something like a low value on dial color, a high value on strap color, so on and so forth. And it would come up with a set of watches which are varying along one particular dimension, but is common across all others. And we then asked respondents to tell us which watch do they want. And we also collected the demographics, things like age, gender, etc. And then we applied it in a utility model to understand consumer preferences on these visual characteristics, and also to understand whether different demographics have different preferences on these visual characteristics. Next, we also had a held out data set, and we wanted to predict consumer choices using our embedding, the disentangled embedding, and compare it with a pre-trained deep learning model which takes the images as input. And we saw that our embedding, even with a fairly non-sophisticated deep learning model at the back end, like a simple hierarchical Bayesian model, was able to perform really well, and it was actually outperforming the pre-trained deep learning model. So this really means that the model is capturing something very basic, which humans probably have preferences on. And our method only found like 6 characteristics. But typically a pre-trained deep learning model will have lots more, typically hundreds of dimensions. So finally, using this conjoint analysis, we wanted to generate like an ideal point for different consumer segments. And we found that essentially in our data set there were 2 major segments. Segment 1 was mostly composed of young, moderately affluent females, and segment 2 was mainly older males. And our model was generating the watch on the left side as the ideal watch for segment 1, and the watch on the right side as the ideal watch for segment 2. So using this, we then wanted to say, suppose this ideal watch would have been available to our respondents, how much choice share would it take away from all the existing watches in the market? And we saw that, just to validate the ideal point, and indeed it was taking a lot of share away from the top 10 watches that were preferred by segment 1. Right, so to conclude, so the method is able to automatically find interpretable visual characteristics. It's able to quantify these characteristics, and using these 2 properties, we can apply them in a variety of methods like visual conjoint, market structure, and product recommendations. We leveraged this property of generating visual designs and applied it in visual conjoint analysis, and then showed how it outperforms even a pre-trained deep learning model, probably because it's able to find human interpretable visual characteristics over which consumers have preferences on.